Hello everyone, my name is David and I'm a postdoc at the University of Calgary. The paper I'll be presenting today is titled Tight Lower Bounds for the RMR Complexity of Ricoeur Mutual Exclusion, and it's authored by me and Philip. Let us start with a short outline. First, I will explain what the Ricoeur Mutual Exclusion problem is. Then, I will briefly describe the related work on the Ricoeur Mutual Exclusion problem. Next, I will give a brief overview of our lower bound and its proof. And finally, I will conclude with some implications of our result and an open problem. So let's look at the Ricoeur mutual exclusion problem. In this problem, there is a set of processes that begin in what is called the remainder section. So these processes I am representing with little yellow smileys. At any time, any process in the remainder section can choose to leave in order to enter another section that is called the critical section. After it has finished what it wants to do within the critical section, this process can then exit and return to the remainder section. What makes this different from the normal mutual exclusion problem is that these processes can clash. When this happens, this process is expected to eventually revive, at which point they will have to find a way to rejoin the cycle. A solution for the Ricoeur mutual exclusion problem must thus specify the code executed by each process for each of these three arrows. We call these arrows the enter, exit, and recover protocols. Now, the resulting executions must then satisfy a few properties. At the minimum, the three properties called mutual exclusion, deadlock freedom, and critical section reentry must be satisfied by the solution. Let us take a look at what each of these properties mean. First, regarding mutual exclusion, we look at the critical section. If, in some execution, there is a time when there are two or more processes in the critical section, then we say that mutual exclusion is violated. Next, regarding deadlock freedom, we look at each of the three arrows. If, in some execution, there are some processes that completely block each other from completing the code in some arrow, effectively clogging it up, then we say that deadlock freedom is violated. Finally, regarding critical section reentry, we look at the critical section again. If some process clashes within the critical section, then the critical section must be reserved for the clash process. No other process may enter until this process re-enters the critical section. In addition to these three fundamental properties are many stronger but optional properties, such as first come, first serve, starvation freedom, and wait-free critical section reentry. But these are not the focus of the video. These are not the focus of the paper, so I will not discuss them within this video. Solutions for the Ricoeur and non-Ricoeur mutual exclusion problem are typically measured by their RMR complexity. Intuitively, this is the number of meaningful shared memory operations that a process can be forced to take in a cycle through the critical section or form a clash. There are two distinct models for measuring the RMR complexity of an algorithm. In the cache coherent model, processes keep cache copies of the registers they have read, and if they later read the same registers again, and its value has not changed, this read would just return the value inside the cache and so does not count as an RMR. Thus, the number of RMRs is simply the number of operations minus the number of repeated reads. In the distributed shared memory model, the processes have ownership over disjoint subsets of the registers in the system. Intuitively, if a process owns a register, that register is local for it. It is easily and quickly accessible. So the number of RMRs is simply the number of operations on the registers that are not owned by the process. Our lower bound will apply to both models. Now, let us discuss some previously known results for the Ricoeur mutual exclusion problem. Golab and Ramaraju presented the first Ricoeur mutual exclusion algorithm. In addition to the standard reads and writes, this algorithm uses the standard primitives compare and swap and fetch and store, and has O log n RMR complexity in the CC model. Golub and Handler then improved on this result, achieving an IMR complexity of O log n over log n. Jayanti, and Joshi then showed that this IMR complexity can also be achieved in the DSM model, and even do so without using compare and swap. A few solutions have managed to go under the log n over log n bound, but with certain caveats. Golub and Handler give a solution with constant worst-case IMR complexity, but this solution requires the non-standard primitives fetch and store, a new primitive oriented specifically for the IME problem, and double word class. Neither of these is supported by current hardware architectures. Jayanti, and Joshi then showed that if double word class is not allowed, O of F IMR complexity can still be achieved in the CC model, and in fact, O of 1 can be achieved in the DSM model. More recently, Katzen and Morrison showed that if W-bit fed and add objects are used, then O log n base W IMR complexity can be achieved in both models. In particular, if W is equal to n to the power epsilon for some positive constant epsilon, then O1 IMR complexity is achievable. However, under the modulistic assumption that the number of bits is polylogarithmic, this only gives the O log n over log n IMR complexity. Thus, it is natural to wonder if this omega log n over log n IMR complexity barrier can be broken using only standard primitives. In this paper, we showed that the answer is no. To do so, we draw inspiration from another omega log n over log n lower bound by Anderson and Kim for the non-recoverable mutual exclusion using compare and swap. Anderson and Kim showed their lower bound by taking any non-recoverable mutual exclusion algorithm and then constructing a schedule for it in a series of high and low contention rounds. In each round, every active process incurs an IMR, and 1 over polylog n of them will survive the round. Thus, there are omega log n over log n rounds, and some process will incur that many IMRs in the resulting schedule. At a high level, the proof of our lower bound will follow the same outline. I will now explain this proof in more detail. For our proof, consider any IME solution that has small o of log n IMR complexity for n processes and uses only read, write, compare and swap, fetch and increment, and fetch and store operations. So without loss of generality, we can assume the algorithm uses only registers that support all 5 of these operations. Our goal is to construct a schedule sigma such that each process crashes at most once, and some process incurs omega log n over log n IMRs. And thus, this will show that every IME solution has omega log n over log n IMR complexity. The main intuition for this schedule construction is that if multiple active processes have not discovered one another, then they cannot safely enter the critical section. Otherwise, this would risk violating mutual exclusion. So we will schedule the process steps such that no active process ever discovers another active process. And if it is inevitable that some active process P would discover another active process Q, then we will complete or remove either P or Q. Similar to Anderson and Kim, we will construct the schedule in a series of rounds such that by the end of each round I, every active process incurred I IMRs. Each round may contain the following phases: a setup phase consisting of non-IMR incurring steps, and either a low contention phase consisting of IMR incurring steps on distinct registers, or a high contention phase with IMR incurring steps and clashes. In the setup phase, we simply allow every process to take non-IMR incurring steps until it is poised to perform an IMR incurring step. But to ensure that no active process is discovered, we have to maintain 2 invariants. First, if P accesses a register owned by Q, then either P or Q has been removed or completed. Second, if P accesses a register that Q is a cache copy of, then either P or Q has been removed or completed. So the non-IMR steps of the setup phase cannot discover other active processes. A low contention phase occurs when the active processes are poised to access a sufficiently large number of registers, i.e., there is low contention on each register. In a low contention phase, we first construct a graph where each pair of processes is connected by an edge if and only if one of the following is true. 1. Both processes are poised to access the same register. 2. One process is poised to access a register that is owned by the other. Or 3. One process is poised to access a register that was previously accessed by another. So let us draw a graph, and suppose this is the resulting graph. We now find the maximum independent set of this graph, which is shown here as the green smileys, and then we erase every process that is not in the independent set. Finally, we allow each of the remaining processes that were in the independent set to take exactly one step. Given this construction, it is easy to see that no active process is discovered, since every process in the maximum independent set takes a step on a distinct register that is neither owned nor previously accessed by any of the other processes in the set. Furthermore, since there is low contention on each register, a significant, but not constant, fraction of the processes will remain. A high contention phase occurs when the active processes are poised to access sufficiently few registers. In a high contention phase, the active processes are divided into sufficiently large groups such that within its group, all processes are poised to perform the same type of operation on the same register. Next, we select two processes in each group, which I will represent here with red smileys, and call them the alpha processes. We then allow each alpha process to take exactly one step, and after which all alpha processes clash. Then we allow all alpha processes to recover and run to completion. During this run to completion, every non-alpha process that will be discovered by an alpha process is erased. This ensures that the alpha processes can run to completion without waiting on any non-alpha process. Finally, we will search for a still undiscovered process in each group, if any exists, and call it the beta process. Now, because the groups are sufficiently large, we can prove that a constant fraction of the groups will contain a beta process. We use blue smileys to represent these beta processes. It is at this point that we face the main challenge for our lower bound proof. Recall that by the end of each round I, every active process must have incurred I RMRs. So if we want the beta processes to remain active, they must be allowed to take a step. But taking a step now is too late. The beta processes would become the last processes to access the registers, and that will make it unacceptably easy to discover all beta processes. So instead, what we will do is rewrite history to include the beta processes. And in particular, we must do so changing the past without changing the present fact that the beta processes were not discovered by the alpha processes during their run to completion. Specifically, we will rewrite history by replacing the first part of our history with a careful ordering of the alpha and beta steps, such that we will reach the same register states that were in the original history. This ensures that after the alpha processes clash, all registers have the same state as in the original history, so the steps taken by the alpha processes during their run to completion remain the same as before, and thus the beta processes remain undiscovered. The way we rewrite history depends on the operation type that the active processes are poised to perform. First, consider the scenario where the processes are poised to perform fetch and store operations. In the original alpha history, the two alpha processes each take a step, changing the state of the register to the value that the second alpha process fetched and stored. Then, as shown in As shown in this diagram, we can rewrite history to include a step of the beta process by making the beta process take a step in between the steps of the alpha processes. As you can see, the final state of the register R is still the value fetched and stored by the second alpha process. This particular rewrite also works for read and write operations. Compare and sort operations can also be dealt in a similar way, a bit with some changes in the ordering. However, fetch and increment requires a different approach. In this diagram, the two alpha processes have incremented the value of the register R twice, and so the final state of R is its original value plus 2. Now observe that if we were to try to insert another fetch and increment operation by a beta process somewhere, the final state of R would inevitably become its original value plus 3 instead. This could cause the present to change. Then the alpha processes run to completion, they could discover that R has a different value, and then take a different course of action that leads to the discovery of the beta process. Thus, we have to rewrite history differently. Here, we will delete the fetch and increment operation of the first alpha process and replace it with the fetch and increment operation of the beta process. Thus, the final state of the register R still becomes its original value plus 2. Now, note that this is safe because the alpha processes will immediately clash and reset their process states. Thus, history can be successfully rewritten to include a step of the beta process in the past without changing the present. As a result of the above construction methods, we can ensure that in each round, every active process incurs an RMR, and 1 over polylog n of the active processes survive. Thus, there are omega log n over log n rounds, and the recoverable mutual exclusion has the same RMR complexity. Now for our conclusion. Our result has shown an omega log n over log n RMR complexity lower bound for recoverable mutual exclusion. This demonstrates for the first time that recoverable mutual exclusion is strictly harder than the traditional non-recoverable mutual exclusion, because the latter has been shown to have constant RMR complexity. Furthermore, Golub and Handler have shown that in the stricter system-wide failure model, where all processes must clash simultaneously, recoverable mutual exclusion can also be solved with constant RMR complexity. Thus, our result also demonstrates that recoverable mutual exclusion is strictly harder when processes can fail independently of one another. Finally, recall that there is an algorithm that uses polynomial bit fetch and add to break the barrier. But they need super logarithmic bits to break the barrier, which is usually not true. And we conjecture that it is not possible to break the barrier using any object of polylogarithmic bit size. We believe we can prove this, so stay tuned. And that concludes this video. Thank you for watching.